In today's functional analysis class, we are going to discuss Banach-Steinhaus theorem. So it is actually a corollary to the theorem 9.1, uniform boundedness principle. So it states that let X be a Banach space, Y be a normed space, and Fn be a sequence in BL of xy such that the sequence Fn of x converges in Y for every x in x. And for x in x, define f of x is equal to limit n tends to infinity fn of x. Part A of this corollary is known as Banach-Steinhaus theorem. F is a bounded linear map from x to y and norm f less than or equal to limit inferior n tends to infinity norm fn less than or equal to supremum norm fn such that n equal to 1, 2, etc. and that is less than infinity. B. Let E be a totally bounded subset of x, then fn of x converges to f of x uniformly for x belongs to E. So we prove this. So first we prove Banach-Steinhaus theorem. Proof. Let alpha equal to supremum norm fn such that n equal to 1, 2, etc. A. We have f is linear. You know that f of x is limit fn of x, and for every x in x, the set norm fn of x such that n equal to 1, 2, etc. is bounded because fn of x is convergent, because the sequence fn of x is a convergent sequence in y. Therefore, by uniform boundedness principle, therefore by 9.1, the set norm fn such that n equal to 1, 2, etc. is bounded. For x in x, we have norm f of x equal to limit n tends to infinity norm of fn of x. So this is less than or equal to limit n tends to infinity norm fn into norm x less than or equal to a limit inferior n tends to infinity norm fn into norm x. We may go through the definition of limit inferior, and we have norm f is supremum modulus of f of x such that norm x is less than or equal to 1. So this is less than or equal to limit inferior n tends to infinity norm fn, and this is less than or equal to alpha, and alpha is less than infinity, where alpha is supremum norm fn. Therefore we have norm f less than or equal to limit inferior n tends to infinity norm fn, and that is less than or equal to alpha. Alpha is supremum norm fn such that n equal to 1, 2, etc. and that is less than infinity. So this proves the Banach-Steinhaus theorem. So here you must go through the definition of limit inferior. Proof of B. So let E be a totally bounded subset of X. Let epsilon positive. Since E is totally bounded, there are x1, x2, etc. xn in E such that E is contained in U of x1 epsilon union u of x2 epsilon union etc. union u of xm epsilon. You know that fn of x converges to f of x. Now fn of xj converges to f of xj as n tends to infinity for j is equal to 1, 2, etc. m. Now since fn of xj converges to f of xj, we can find an n naught such that, so find an n naught such that norm of fn of xj minus f of xj is less than epsilon for all n greater than or equal to n naught and j is equal to 1, 2, etc. m. So this is possible since fn of xj converges to f of xj. Now choose an x in E. Let x belongs to E and choose xj in x such that norm of x minus xj is less than epsilon for all n greater than or equal to n naught. And this choice also possible since E is the union of u of x1 epsilon, u of x2 epsilon, etc., u of xm epsilon. So we have norm fn of x minus f of x. This is equal to norm fn of x minus fn of xj. Add and subtract fn of xj. So plus fn of xj. Now you add and subtract f of xj. So minus f of xj plus f of xj minus f of x. So this is equal to norm of fn of x minus xj plus fn of xj minus f of xj plus f of xj minus x. So this is less than or equal to norm fn into norm x minus xj plus norm fn of xj minus f of xj plus norm f into norm x minus xj. So this is equal to norm of fn plus norm of f into norm of x minus xj plus norm fn of xj minus f of xj. You know that norm fn is less than or equal to alpha plus norm f is less than or equal to alpha by part A into norm of x minus xj is less than epsilon plus you know that fn of xj converges to f of xj and fn of xj minus f of xj is less than epsilon. So this is plus epsilon. So this is 2 alpha plus 1 into epsilon. This implies that fn of x converges to f of x uniformly for x in E. Hence, fn of x converges to f of x uniformly. For x belongs to E. So this proves that theorem, and that's all for today.